Once again, hi everyone. I'm Jahanzeb Tariq. You can also call me JT. One of my 19 nicknames. And I'll be here thanks to Jacob talking about decarbonizing heat through life cycle. And that will be throughout the entire life cycle of a heat pump, essentially decarbonizing heating through electrification, and then looking into embodied carbon and how can we enable decarbonization of embodied carbon through circularity, which is further enabled by digitalization. And that's when I'll be talking about the IEA project as well. One disclaimer, the numbers that you might see in the presentation are not yet third-party verified. We will get them verified through a third party so that we can, publish them publicly. Moving on, this is the heat pump that I shall be talking about. You can see this beautiful outdoor unit in the black out there. And you can see also equally beautiful, the white indoor unit within the building. This is the star product of Viessmann. We call it 50A. Works very quietly and is essentially supposed to decarbonize heat like no other. Moving forward, this is how the indoor and the outdoor unit look like. For people who are familiar with heat pumps, would be not surprised by the slide. You see that the indoor unit is has a buffer tank, has a diaphragm vessel, water and water pump, while the outdoor unit contains the refrigerant, the refrigeration circuit, containing accumulator, compressor, electronic inverter, all sorts of copper pipes, fan, and metal sheets, of course, to surround and make it look more beautiful. Moving on, while this is more of a picturesque view of the heat pump, this is a bit of an ugly view that you will see. Again, for people who know or who have been dealing with heat pumps, this will come as no surprise, but the pictures, this is an outdoor unit, stripped naked. And the reason why I show this is to kind of identify the complexity in materials components that make up and assemble the outdoor unit of a heat pump. So similar components that we talked about before, fans, you see some electrical gear there, electrical circuits, you see certain a compressor, a condenser, and so on hidden under insulation. This is the indoor unit that you see. So similar diaphragm vessel is something that you see here. Maybe I can turn on the pointer. There we go. So essentially here you see the diaphragm vessel, the buffer tank, and then the circuitry connected, which goes in connection to the outdoor unit. Again, the idea of showing this picture is how complex this product is in excuse me, in number of materials and components. Moving forward, I want to address a little bit about the supply chain. The supply chain for a heat pump manufacturer are never easy, and there is a tier of suppliers that goes from the manufacturer up to the tier 0 supplier. Let's say if I want to have steel, it will go back up to the iron ore extraction if you take into account the life cycle perspective. So we segregate or we divide our suppliers into 4 different categories. One is the raw material suppliers. For example, if I get a steel coil as a raw material, I take that coil, I cut it, I bend it, I powder coat it, and then I put it and assemble a heat pump out of it. So basically, the upstream value chain that the raw material supplier is going is that once the iron ore is extracted, if you look top down from here, once the iron ore is extracted from the ground, it takes to a processing and refining facility to turn it to the steel grade that I want, and then through the raw material supply is provided to my factory. Another kind of material that you might get, we call it third-party raw material supplier, which is essentially raw materials such as nuts, bolts, screws, gaskets, and so on of different metals, thermoplastics, of different materials, and excuse me, and are basically worked upon into a final state where I can use these components to assemble a heat pump or assemble a product that I make under my roof. They have an added layer after the raw material supplier. So for example, the copper or the aluminum or the steel that the supplier gets and turns it into a bolt or a nut is one step further into the tiers of suppliers. Moving forward, the third category we identify as third-party finished component supplier. For example, if you buy our our condenser or heat exchanger from a supplier upstream, we don't know what goes in as consumables. For example, electricity, natural gas, testing gases, welding or powder coating, or certain amount of water consumption. Simultaneously, also the material that goes in and the material efficiency of the product, of the component that comes out of our supplier's factory. We take this component and we put it into a heat pump, and essentially it functions according to the specifications that we've identified to our supplier. So you see that this little staircase is getting more complex as we go down to more towards from raw materials to finished components. And the last but not the least, of course, is the OEM supplier, that we buy components or we buy products and we combine them with our manufactured products, and then we essentially sell them on the market. So with each category of suppliers, the complexity gets more and more. The number of tiers of the upstream suppliers gets cascaded. And with this cascadance, if we want to assess the upstream life cycle of a heat pump, it gets more and more complex, reminding you of the pictures that I've shown of the two indoor and outdoor units having a variety of components and materials. Moving forward, if you look at the life cycle of a heat pump, essentially the material is extracted from the ground, it is refined and brought into a grade of purity where it can be used. And then through either the four categories of suppliers, it is transported to our factories. In our factories, it is worked upon. There is a certain waste which is minimized and repurposed to the extent that it can be. And then it is put onto the market, sold to the end customer. We then have certain digitalization. We have some digital infrastructure. We call them, for example, the Viessmann app for partners and consumers, and then the Viessmann Spare Parts app. That is essentially there to help our customers have better operation and maintenance. Through those apps, they're able to prolong the life of a heat pump. So, for example, if a heat pump is expected to last 12 years, it might last longer because of certain replacement of components and proper O&M service. Finally, it reaches end of life, and then the product is decommissioned. Once the product is decommissioned, it can go towards business as usual end of life recycling. For example, steel, copper, aluminum, all the metals have a very good business case. So it is expected to go into that stream of end of life. It could be disposed, for example, it could be disposed into a landfill where it sits there for hundreds of years. The material, depending, for example, thermoplastics, rubber, insulation, some parts of metals as well. And then it could also be brought to an incineration facility where it could be incinerated to recover energy from it. For example, you burn plastics or you burn insulation to produce steam that might run a turbine to produce electricity, or it could be burnt without energy recovery, depending on the energy value of the material. So that's essentially the life cycle of a typical heat pump. It could also be sold on the secondary market, either within European Union or outside European Union. If you Google, or rather, if you go to eBay Kleinanzeigen, and if you go and you put Viessmann there, you might see certain boilers being sold secondhand. Having said that, if you look at the excuse me, if you look at the upstream value chain, and if you look at the four different categories of suppliers, you might find a number of materials and finished components. For example, copper pipes, steel that could be carved into the needed shape and formation. Electronics, so printed circuit board, something that we make ourselves in factories in Allendorf. Put S&D components on top of it. A water pump from our suppliers in a finished component state. Copper pipes sitting with insulation, fans, compressor, condensers, thermoplastics, and so on and so forth. That's essentially a cascade of different sorts of materials, components that are coming to our factories to make the final heat pump. Going further, if you look at the mass share of the indoor and outdoor unit, first you can see the clear demarcation between the mass difference of the indoor and the outdoor unit. The indoor unit roughly weighs around 50 kilograms, while the outdoor unit roughly weighs around 250 kilograms. By the way, these masses are inclusive of packaging, and that you can see here, for example, 7.8% of the outdoor unit mass is packaging, and for 20% mass is percent of the indoor unit mass is about packaging there. And this reminds me of a very interesting quote from one of our installation partners regarding the mess that the packaging can create once you install a heat pump, but takes about anywhere between 3 to 7 days. He says, getting a heat pump from Viessmann is like a Christmas, but I don't want to have Christmas every day because I have to deal with packaging mess once I install it. And the percentage mass kind of speaks volumes on top of it. Okay. Having said that, the reason I put this slide here is you can see that in both the indoor and the outdoor unit, the biggest percentage share is by metals. This metal can be steel, can be iron, cast iron, can be aluminum, copper, and so on. And the next big then comes across from third-party finished components. That could be a condenser, could be a compressor, could be an evaporator, and so on and so forth. Having identified what the heat pump is made up of in terms of materials and components, we look at the geographic variability of the heat pump. This particular heat pump is essentially made within 3 factories in Europe. So in Germany, we have Allendorf, where our headquarters are, and we assemble the indoor unit. In Poland, in Legnica, we have the outdoor unit assembly. In France, we do have certain components coming from Fulquimont in France that basically come to Germany and are being assembled to the indoor unit. And from China, of course, that's the biggest mass share third-party component purchase that we do, that we purchase from there. Rest assured that there are more number of suppliers, and there are, of course, more number of countries from where the components, as small as it may be, are coming from for this particular heat pump. So what we've discussed until now is essentially the material variability, the temporal variability of materials coming from different the geographic variability of materials coming from different supply chain routes, and also through different transport mediums and from different parts of the world. Having identified that, I'll talk a little about the CE RISE project now. Once we understand the heat pump, it is also critical to understand to keep trace of these molecules from an upstream value chain perspective to use phase to downstream value chain perspective. Because having a digitalized tool helps us to keep track of these molecules, whether they might be in a compressor, whether they might be in a steel sheet, or in a thermoplastic. So what the CE RISE project is essentially trying to do, which is an EU-funded project, part of the Horizon 2020 to 2027 project, is trying to enable circularity in different products through a digitalized infrastructure, which is based on blockchain technology. So if you look at the life cycle of a typical product, whatever it may be, extraction of material from ground, refining in material production, and then transporting to the manufacturer, having it in the use phase as long as the lifetime of the product might be, reaching end of life, and then decommissioning. Ensuring having a digital infrastructure on top of it can help us close the loop from the end of life pathways to the upstream value chain again. And that could be done by data-driven decision making. That is something that the CE RISE project is essentially working on. So how it is able to do that is basically developing a digital product passport of the said product, let it be a heat pump, for example. So I show you a similar life cycle that I showed before, and you can see that here, excuse me, you have the life cycle inventory, or the LCA data, which is also now to be mandated for, or rather regulated by the European Union for the manufacturer to make public. For example, the critical raw materials, or the strategic raw material identification, the PFAS identification, conflict minerals, 3TG, rare earth metals, rare earth magnets, hazardous materials identification, also compliance to ESRS, section E4 and E5 on material efficiency, and so on and so forth. So the DPP, or the digital infrastructure that the CE RISE is working on, will have, in an ideal world, the capability to carry this information and enable the communication between upstream value chain stakeholders and downstream value chain stakeholders. Moving forward into the into the life cycle, once the product is sold on the market, a certain set of information needs to be made public, which we do already. However, having that one single source of truth clears a lot of noise for different stakeholders across the value chain, that enables better communication through ZRISE project. For example, talk about the product information, can have the energy label and eco design, can have the maintenance checklist, can have the product data sheet, product warranty, compliance to ROS, REACH, and V directives that manufacturers already have, but having that stored in the single digital box enables better communication between different stakeholders. And similarly, details for customers, purchase history, repair and maintenance history, especially relevant for products that have a second life, and certain circular strategies, or as we like to call them, RE strategies, that could be enabled through that information across the life cycle. Coming towards the end of the life cycle of the product, the right decommissioning instructions from the manufacturer or dismantling instructions, understanding the value in certain components. If you talk about the heat pump, for example, the heat exchanger, the compressor, the evaporator, the refrigeration circuit, copper pipes, for example, have a very high value in terms of recycling. Identifying the value, connecting it to the right end of life stakeholder could help us connect the end of life value chain back to the upstream value chain. Having said this, some of our suppliers already have an active take back system where they are willing to pay to collect their components back, take them back to the factory, and essentially provide implement the 5R principle to earn revenue from circular business models. Having a digitalized infrastructure could help facilitate that, to make it on a higher scale. That's essentially what ZRISE can do. Having all of that information embedded, having the ability to perform life cycle assessments, having the ability to measure the circularity of a product, and enable different stakeholders across the value chain again, to implement resources to the extent needed where it's cost profitable. Having said this, if we look into an ideal world where ZRISE is operating, you look at the downstream value chain and go back to the heat pump that I just discussed in terms of mass share, in terms of component share. There are certain end of life value chain, again, imagined or theorized, where the maximum benefit out of those materials could be extracted, and that's what I've displayed here. And this will be the basis of certain decarbonization calculations that I'll show during the presentation. So, excuse me, having looked at the life cycle emissions, the V2CAR 250A essentially has 17 tons of CO2 in its life cycle emitted, and this is when the heat pump is operated in Germany, not in any other country, because each country has a specific electricity emission factor, and that emission factor will vary if you go to France or if you go to Poland. I'll also display that in later slides to come. So that's why demarcating that the LCA that is done is taking into account the German electricity mix. So the embodied carbon, or the carbon from cradle to the output gate of the factory, is essentially around 2 tons. The transport of the heat pump to within Germany is around 148 kilograms of CO2 equivalents. And then the transport of the materials to the Viessmann factories are 148 kilograms of CO2 equivalents. The manufacturing at Viessmann has very low impact on global warming, somewhere around 48. The use phase is essentially the highlight, which is around 15 tons. Of course, if you look at a heat pump working around 17 years, operating for 17 years, taking into account the decarbonization of the German electricity grid, about 15 tons of CO2 would be emitted. And in the end, looking at business as usual, end of life disposal pathways that I've just seen through which could be enabled through ZRISE, of course, is around 150 kilograms of CO2 equivalents. So the hotspot is essentially the use phase, which is 15 tons of CO2. And as per the title that I showed at the presentation, we have to decarbonize heat along the life cycle. And use phase is, of course, the highest, the highest in the life cycle. If we operate a heat pump in different countries, in different regions, we realize how the impact of the heat pump can vary, and we compare that impact with the residential natural gas boiler. So looking at how low the impact is in France, how low the impact in Germany compared to Poland, and then compared to natural gas boiler. So as the electricity, and you can see that the yellow part of these graphs essentially showing the use phase, um, showing the use phase is increasing while the rest of the life cycle share is standing still, because the embodied carbon and end of life could be similarly treated in at least within European Union. So as the emission factor of the grid increases, we go very close to having a life cycle emissions of the residential natural gas boiler. So looking at the heat pump operated in Germany, and this is about 20 years of lifetime of heat pump being operated, you see that around 17 tons of CO2 is emitted throughout the life cycle. And you see that as we move into the future, let's say from 2024 to 2025, you realize that the share of embodied carbon is increasing and the share of operational carbon is decreasing because the electricity grid is decarbonizing. Simultaneously, the end of life share is also increasing, provided that both the numbers are kept constant. So in percentage, we do realize that the embodied carbon is going to increase if we keep on. Is there a question there?
I think we just had another one joining in, so that was the reason for the sound.
Okay, it's been awfully quiet, so either, I thought I was disconnected or no one was listening, but that's good to know. Yeah, so just going back to the train of thoughts, the embodied carbon is increasing percentage while the grid is decarbonizing. How do I affect the red part further? Because having the grid decarbonize is essentially an externality that I cannot influence. So how do I influence the use phase where I, as a manufacturer, have very less influence on? How do I decarbonize that use phase? So if you see here, this is excuse me. Another heat pump that is operated. So I put the slide there, which is not essentially for Vitocal 250A, but I just wanted to essentially show that influencing the use phase by having a PV and a battery in a household, for example, on the rooftop, you have a certain installation of PV, and in the basement or in the garage, you basically have a certain battery that allows you to have a cost-effective utilization of your electric and heat loads, but also decarbonize your heat pump operation. So, excuse me. Again, in Germany, we have, let's say, the heat pump essentially has about 28 tons of CO2, which is a different heat pump again, to highlight again. You increase the PV up to 10 kilowatt from zero, and you have a battery for about 8 kilowatt hours. You almost go towards half and half of CO2 emissions throughout the life cycle. This is, by the way, also incorporating the life cycle emissions of a battery and a PV as well. So logically, if I increase the PV system up on my rooftop, imagine that I have a villa, which I don't. And if I increase the battery as well, logically, the emissions should decrease within the same order. However, you see that if I double the PV and I almost double the battery, the decrease in CO2 is not as much as the first jump that I showed. So from 28 to about 17, and then from 17 to roughly around 13. And this is happening because the PV generation has a different load profile, has a different generation profile. The heat load through a heat pump has a different load profile. This is something that I can show here. So in the black that you see is a typical heat load or a heat pump operation consuming electricity. And in the yellow graph, you basically see a typical, very idealized solar PV generation profile. If I go further, you see the yellow area graph now is direct consumption of PV for the heat pump load. So this is offsetting grid intake and is essentially decarbonizing my heat pump operation in the use phase. Imagining having a battery there as well, since I have excess energy after meeting the load of my heat pump, I can store this into a battery. So the green area graph is essentially showing you how my energy is going into the battery after having met the load. So that's kind of the merit order. Meet the load first, charge the battery afterwards. After, excuse me, after the battery charge and it has reached its 100% or 90% state of charge wherever I have a set point of it, I still have PV generation, and that is essentially what I sell to the grid. So on the negative y-axis, the yellow area graph that you show is essentially I'm selling excess solar PV to the grid, and I'm making sure that I'm making money off of it no matter how less it might be. When the night falls and the sun is not shining, the red area graph is essentially battery discharge, which is essentially meeting the load that I have through PV stored into my battery. So the night loads are also in that point of view decarbonized because I utilize my battery to charge my loads. So what I've left is essentially the morning time or the night towards the morning time where my battery is empty, the sun is not shining, and I utilize the grid to essentially make use of it. And so no matter how big of a PV I put, no matter how big of a battery I put, if I want to be cost effective, I will still be dependent on a percentage share of grid that will be meeting my loads, whether it be electrical loads or the heating loads. And that's why I'm dependent on that externality and can influence my use phase to decarbonize to a certain extent. I can put virtually a very big PV on my rooftop or in my backyard. I can have the biggest of the batteries. But then if I meet 100% of my load, calculations show that I'll not be cost effective. Hence, having a little grid makes my purchase rather cost effective, and I'm able to decarbonize a significant part of my energy consumption. So coming back to this graph now, and what I've done is now I've highlighted, since as a manufacturer, although Viessmann offers PV and batteries alongside our own developed home energy management solutions, which is smart energy management, how a battery talks to PV and how a PV talks to a heat pump, and how they all talk to the grid. It is not affordable by every household across Europe or across the world. So as a manufacturer, if I want to decarbonize my value chain, the biggest influence I have is essentially the blue part, which I can influence by talking to my upstream suppliers, which I can influence by essentially making sure that the end-of-life stakeholders are connected, are well informed so that the material flows are connected from end-of-life to my upstream value chain again. And that part is essentially 2 tons of CO2, which is, if not too high, is also not very insignificant. And also what this graph is showing is if after 10 years or after 11 to 12 years, if I'm putting a heat pump on the market, the embodied carbon is but a significant part, up to 50% of my CO2 that essentially that is allocated to me as my scope 1 and 2 when I put the product on the market. So embodied carbon will become more and more relevant as we go into the future because we know that the grid is decarbonizing across countries. So coming back, if I look into my heat pump and I've shown certain pictures of materials and components of what the heat pump is made up of, this is the LCA done for my components that essentially make up the heat pump. So you can see that AC choke, PCBs, and steel are the biggest hotspots alongside evaporator when it comes to having the embodied carbon share. And this graph tells me where I need to focus on, which suppliers I need to talk to, and also which end-of-life stakeholders I need to talk to essentially make sure that I decarbonize my embodied carbon. Moving forward, ensuring that C-RISE in an ideal world is working, the DPP and the blockchain-based infrastructure is enabling the value chain stakeholders to talk to each other. In an ideal world, I can apply the 5R principle, which is essentially reuse, refurbish, remanufacture, I can increase repairability, and more importantly, I can recycle materials and components that have high mass share, or rather have high embodied carbon. Again, this is a slide that I showed before. Now, since I moved towards numbers, I wanted to show the slide again. And this is, by the way, an ideal scenario. So I know that there can be questions on saying, okay, how can 95% of metal can go to scrap sorting for recycling? We have both numbers. We have taken 70% as well. We have taken 95% as well. And the idea is to show you that how in an ideal world, a digital infrastructure can influence the decarbonization of products. So if I have a circular value chain, if I have a digital infrastructure that enables the circularity of my value chain, so I move forward, I extract my material from the ground, I process and refine it to the right grade and purity. I put it into my product and manufacture the product, put it on the market for use phase, and then they're end of life. So from scrap sorting, either I can go towards incineration with and without energy recovery, I can go towards a recycling effort, or I can put certain things into the landfill. And if there's a recycling effort, there will be a transport that will go back to, for example, the steel is recycled and it's transported back to my steel supplier.
Yeah, partners can fine tune that.
Sorry? Is there a question in the room, or?
I think that somebody missed to put on the mute while talking.
Okay.
So
Okay.
Yeah.
No worries. These hiccups always tend to give a sign that the call is still there or someone is listening. So that's good. Yeah, so from a recycling effort, the transport will go back to processing and refining. For example, my steel supplier can take in scrap, and a certain percentage of scrap could then be allocated to decarbonizing and decoupling from virgin material extraction. Our suppliers already have EPTs on the market. For example, talking specifically about steel suppliers, have EPTs on the market on how the CO2 emissions per kilogram of steel is decreasing while the scrap into their mix is increasing in percentage mass. Okay. So just taking that example forward, I wanted to put some numbers, and then I'll especially for all the steel in the heat pump, and then we'll basically go on towards showing how the whole of the product as a heat pump benefits from circularity in terms of decarbonizing the embodied carbon. So steel, of course, the iron ore is extracted from the ground. It's going to be processed and refined to producing a steel grade. And until then, it has an embodied carbon of 194 kilograms of CO2 for each 103 kilograms of steel that is in V2CAL 258. After the use phase, the scrap sorting can take certain effort that can have an impact on the environment, as negligible as it may be. We say 5% of that scrap goes to landfill, but the rest is essentially going towards the recycling effort. The recycling effort has, has a certain impact on the environment, so 30 kilograms CO2. The basis for the calculation of these numbers is EcoInvent database, by the way. And if this is transported, again, taking a rough estimate of about 100 kilometers, this is taken from the PEP Eco Passport EPD. We can also change that number. The transport emissions are all added, and we see the circularity benefit, having this embodied carbon from virgin material extraction, summing up all the impacts through the later part of the life cycle, including the recycling effort and the transport. We see that we get a benefit by decoupling virgin material extraction by 150 kilograms of CO2. Applying the same method on the whole heat pump, this 2 tons number might be familiar now. The transport, the manufacturing in Viessmann factories, transport to the end user, the use phase, and then end of life. So providing the recycling effort and applying the 5R principle, we realized that about 1,134 kilograms of CO2 in embodied carbon could be reduced because of applying the circularity principle or the RE strategies, and this is roughly around 54% of reduction in the embodied carbon. And if you remember the graph of embodied carbon use phase and end of life, where the use phase was essentially minimizing because of decarbonization of the electric grid, this is a huge win if circularity is in practice. Another catch, of course, is, and again, this is not just a sustainability metric-based decision, but also procurement cost and also availability of the right component. If we are able to avoid purchase of certain components from a country, might it be China or as far as China, we are able to avoid the transport emissions, assuming 19,000 kilometers with a ferry, taking those components to Europe and to Germany, we can avoid about 130 kilograms of CO2 equivalents. Add this number to 968, and this gets more than 60%. So more than half of the embodied carbon essentially could be reduced. That's it from my side. I appreciate you all listening so intently and also patiently, and apologize for the coughing again and for my voice. I'm open for any questions that might come my way. Thank you very much.
Thank you, JT. From our side at least, you went through quite well and passed along a very interesting presentation, and with some very both interesting perspectives and results. I've noted down a question, but I will leave the floor for other people first. And I see that we already have one from Pietro from RISE. So Pietro, will you state your question?
Yeah, thanks for the presentation. It's a very interesting work. As I understood, this result can be communicated to the consumer also, this performance that you show. And one thing that I don't understand is how can you trace that the producer is recycling the same steel he has produced? Is this done with the blockchain methods, or how can you do this?
Yeah, that's a very good question. For steel, it's not yet done. As I mentioned, in an ideal world, right, this could be done, but also in an ideal world, I'm married to Elizabeth Olsen, so that's a bit far away. Coming from the PV industry, what I can tell you is we basically have done it before, essentially combining end-of-life treatment of certain semiconductor that would go back into manufacturing of a specific PV module. You can Google for solar, and then that's what you realize how tellurium is essentially going back. So that's a very good example. For steel and for any other material, it's not yet done, but is envisioned to be done that way. That you have proper certificates ensuring that the end-of-life molecule was brought back to the upstream value chain and essentially was well recycled indeed, and went back to the next batch or next generation of products that were manufactured by the same manufacturer. So, but that's exactly what C-RISE is working on. It's a work in progress. The digital infrastructure is work in progress, and that's the outcome. That's the vision for, of course. Yeah. I hope I answered the question.
Yeah, perfectly. Thanks a lot. The project is really interesting.
So yes, and thank you, Pietro, for the questions. The question here. Does anybody else have a question? I don't see one right now. Oh, I see Ned Pickett.
Yep. Yes, it's
Please.
Ned Pickett. Yes. Hi, Jahanzeb. I'm wondering if you end up just using recycled material and maybe not the full circularity element, is that still reducing your embodied carbon? Because I know you're talking about a real world scenario.
Absolutely. But finding that recycled material is a bit hard. I mean, when you talk about heat pumps and so on, I mean, one of the biggest conversations we have in Europe or maybe in the US as well is about green steel. And put a bit of background, the German Association of Green Steel, I was in the conference back in 23, and what they claimed was something kind of completely out of the box. What our suppliers told us is that they will come back, they came to us and they say, okay, if you lock down a certain volume that you're going to purchase from us, we can then provide you a price of how much your steel is going to cost you when it's green in total. And steel, by the way, makes up 80% of a heat mass of the mass share of a heat pump.
Yep.
So ensuring that there is the claim of the supplier is actually true on scientific basis is never easy, or because of two reasons: tracing back supply chains, but also the calculation that needs to be done is super complex. So what we're trying to do is trying to get those low-hanging fruits. And of course, certain industries such as steel or copper are kind of more under the lens of EU because of their wide variety of applications. Similarly for aluminium, but procuring that recycled content is also sometimes not cost effective. I have certain numbers that I can't disclose from our suppliers, but sometimes it just breaks the business case. Might it be for metals or also for PCBs or thermoplastics and so on and so forth. Yeah.
Thank you.
And thank you, Ned. Any other questions?
Hi, JT. Thanks for the nice presentation. Rachel from ANSYS. I was wondering if you have done any similar scenario that you just presented for the recycling for a reused component in the, or if this is not a feasible scenario for you.
Thanks, Rachel. Depends what components can be reused. There is a law that basically makes suppliers and manufacturers mandatory that if you're going to put a product on the market or component in the market that will be reused or was refurbished or remanufactured, it should be stated. The complexity that arises with it as a manufacturer of a component or of the final product that's going to the market is, can you provide the warranty on equity basis for a new product and a reused product? Can the warranty work that way? Because under warranty, if my product breaks or malfunctions, it's on my cost. And the probability of a reused components, speaking very vaguely, breaking down during the lifetime or the expected lifetime is a bit more. So it depends what component could be reused. For example, in the niche example of a heat pump, we do have certain suppliers who are making money now, who are basically generating revenue from reused components or from circular business models. That's the complexity that it arises with. So to use that assumption that my heat pump will have a reused compressor or reused evaporator or a water pump could be a bit tricky. So that's why the calculations are done mostly on a bit more realistic scenario of recycling certain metals that already have a business case within the European Union. I hope I answered the question, Rachel.
Yes, sure. Yeah, you answered. Thank you very much. Yeah, I understand the complexity. Yeah.
Thank you, Rachel. Any other takers on questions? Okay, I have one here noted down, JT, because you very nicely explained in the beginning that you're seeing the complexity arises when you go through more tiers of suppliers. But do you also experiencing the task being handled by these third-party finished component manufacturers, that they can increasingly provide the information compared to earlier, or what's your perception on that? Is there an involvement in having these data available?
Yeah, that's a bit of a pain point, Jacob. And apologies if I cried during the answer. Unfortunately, it's never easy to get data from upstream suppliers. Since we have suppliers all across the globe, what I can tell you is that suppliers in China are way more efficient than suppliers in Europe in providing the data. May it be also EPDs or LCA calculations. For the heat pump that I've shown, I have data of how much electricity goes into one compressor. So we took our time to contact our suppliers, and it's not just dependent on suppliers, it's also dependent on your own procurement team. Your own procurement team also needs to understand the significance of these questions. They need to frame the question correctly, and they need to essentially provide the right answers with having that particular sustainability professional in the call or at the back end when a supplier answers questions of, okay, like why do I need to provide the data, and what kind of data needs to be provided? For example, the PFAS regulation. We don't know where PFAS is in our components. How can we know? Because we're buying certain components from our suppliers. The funny thing is they don't know as well. So it cascades, goes back to the upstream suppliers. So we do get data, and we have to work very hard for it, because our suppliers are also into a bit of a learning journey. Some of them are very far, like they've progressed really well, like Danfoss or Wilo. Some of them are still lagging behind. We learn from some of our suppliers, and we transfer the knowledge to some of the suppliers that are a bit far into the journey, and a bit behind into the journey. So that's why it's never on one level, and it's always very complex from supplier to supplier. But we do get data. The question is the manufacturer willing to implement time and cost resources into that questionnaire?
Makes a lot of sense. Yeah, it was, and I know it's a multi-layered question, but it was just interesting to hear your perception on that. Marco, you have a question as well?
Yes, thank you. Thanks again for your very interesting presentation. And my question is not strictly related to what you are doing on material itself, but just to have a broader overview and also having the possibility to collect your vision about another aspect. You clearly stated that the most emissions are related to during the working life of the units. And from one side, there is a decarbonization of embodied electricity, CO2 embodied in the electricity. That are you considering to have the possibility to improve efficiency during the lifetime of the units itself, maybe via software, so adding much more performing software, or collecting data from the units itself in order to learn how really those units working there, and having the possibility to increase the efficiency in order to contribute also eventually as a service, because the benefit from the end user is to save electricity and to save money. It's not a service that you consider to provide free of charge, or with minor adjustment, for example, replacing a fan of the outer unit that is close to the end of life with another one that is much more performing in charging slightly the end user for this improvement. Thank you.
Yeah, it's a very good point, Marco. Thanks for raising this point. The answer is not simple. It is in the benefit of the manufacturer to essentially prolong the lifetime of the product. I will talk specifically of heat pump, because if you talk about other products, then the conversation goes a bit vague. Manufacturers do earn a lot of money through after-sale service. So for us, repair is replacing a component within a heat pump. If the water pump is malfunctioning or has reached its end of life, compared to the 12-year lifetime or the 17-year service lifetime of a heat pump, the water pump might have between 3 to 4 years of lifetime. If I replace that, I'm replacing a water pump, but I'm repairing a heat pump, right? And that water pump is earning me revenue, as I showed on one slide from the spare parts app that we have, right? But do I want my heat pump to last in an ideal world 40 years? Probably not. That's cannibalization of the market. I could upsell to the customer more and more. And that's a balance that you need to create in your business models. It completely depends on what kind of business are you in. Viessmann also provides heat as a service, where we provide leasing of a heat pump to our end customers. So you're not paying upfront that heavy cost of 40,000 euros when you install a heat pump, but you're paying per kilowatt hour or per quarter or per month of a specific lease that you have in the agreement that you have with us, right? In that business model, it makes complete sense that my heat pump lasts longer, because if it breaks down, I have to provide another product because my agreement with my customer is on kilowatt hour basis. So, but companies or conglomerates cannot essentially survive on completely leasing or completely third-party ownership business models. There needs to be a balance. And then there's a lot of corporate science involved in that as well. Do my CFO likes to have certain products on the balance sheet that are a liability? So the conversation can go long and long into that, but to summarize, it depends on the business model, and it depends on how much of my revenue can I put at stake to essentially have the next batch of products on the market. So to an extent, yes, but then I don't want my heat pump to last 40 years at the customer side. I hope I answered the question.
Thank you.
Thank you, JT. I think, yeah, we're 1 minute past the mark on 4 p.m. and I see that already some had already had to leave, and I can see more leaving now. So I think from my side, I would like to express great gratitude for making this presentation and for everybody participating. And I believe that it's a very significant contribution you have provided here, and would like to express my gratitude on that. And I will just like to say good afternoon to everybody, and take care, and reach out to me if you're interested in any more.
Perfect.